right, so we reached the final lesson, final class, and of course not the end of the material we wanted to cover. So essentially we sacrificed some of the interesting parts of information theory, which I only highlight in the second hour today a little bit, just to get some of you some idea of what's going on there, and the hope that those who really need it or want to understand more will take another class, another course somewhere, maybe even a course that I will give on information and control, maybe at some point in the near future. But so I don't just want to end what we started to talk about in terms of what we call sample or complexity bounds. Which again I want to repeat what I said, that they all have essentially the same type of structure, that the probability that the distance between what we call the generalization error or the average expected error minus what we call the training error over some sample of some hypothesis, this probability over samples that are taken from any probability over the sample space, the probability that this is larger than epsilon is bounded by usually something which we call the complexity function, or the complexity term, which in general has this structure of the cardinality of H, but we actually extended it to things which are not finite, which are called the complexity factor, complexity term. So this is really telling us essentially how complicated our hypothesis class is, where H is of course taken from. So in some sense, this is we want to say something about the worst case, the supremum in our class. So that H is, so this is the supremum. I just want to emphasize this. And so the probability that the worst possible difference between the training and error and the generalization error, which is essentially this the width of this tube between the red and the blue curve that I drew many times. So the supremum over all the S's, where the probability is taken over samples. The probability that this is larger than epsilon is bounded by some complexity function multiplied by what I call accuracy function, or a bound which usually has this type of form, some constant n epsilon square, maybe some numerical constants here, like over 2, over 8, over 4. I mean, a constant, I don't really care about this. So this, essentially, this is really, and this is what we call the accuracy term. And as I said, I mean, this can be, we want the whole thing to be smaller than some delta. So this I usually write, I can write as put everything in the exponent. So it has some log of the complexity minus some sample function that depends on epsilon. In general, I wrote even a different function here. It can be some monotonically increasing function of epsilon. It can be epsilon or epsilon squared. This is the most common case is epsilon squared, because it's coming from the central limit theorem, from the Gaussian distribution. Right? But there are some special cases when this can be epsilon, like the realizable case, or this can be other functions of epsilon. So this n times some function of epsilon, which a function of epsilon, this is a positive and monotonically increasing function of epsilon in most cases. Okay, so, and this is the general, and this is actually may not be simply the cardinality term, so we write it as some sort of an effective entropy, which may be a function of both n and epsilon. And this is some sort of an entropy or complexity to generalize this notion of low cardinality. Entropy, in this very specific sense, it's this low complexity term, and this has a general, it may in general depend on epsilon and or n. So this is really the general structure that I want you to have in mind. And of course, in order to have a generalization bound, we want uniform convergence in the class, which means we want this worst possible error in the class to be smaller than some delta. So usually we have epsilon as the accuracy parameter, how close the generalization is going to be to the training error for any hypothesis. Since we want to, if you are able to do this to bound the supremum in the class, or the worst possible distance between them, then we are fine. Now, in general, we can relax these things in many ways. I showed several ways of relaxing this notion of complexity. One of them was by this idea of epsilon net, to cover the class with a finite grid of close enough points to my hypothesis. The other one was some sort of a compression, like Occam razor, which essentially generates hypotheses. It can be complicated, more and more complicated, when I get more and more data. So essentially, it's an infinite class of hypothesis classes, if you want, and some sort of hierarchy of hypothesis classes, which we are going to say today is related to the notion of model order estimation or complexity, how to choose the best possible class. Essentially, this is the kind of bound that we always get. And the details are really what can we say about this, and what can we say about this function. And in general, as I said, it's epsilon square is the most common one, because we usually bound it with things like Hofting, or essentially use the Gaussian distribution to bound the tails of large deviations. So this is where the epsilon square comes from. So this I want all of you to remember. I mean, the details are details. Now, details which are important if you really want to understand, but after you understand them, you can forget them. So essentially, this is giving us some sort of a competition between complexity and accuracy. And as long as this entropy grows slowly in terms of n, then n itself and or epsilon, such that I can eventually make this as small as I want, which means that I can make this negative eventually for a large enough n, then I'm fine. Then I can learn. This is the thing I want you to take with you. Now you can take it to statistical mechanics and calculate this type. This actually looks very much like some sort of a free energy. It's a competition between complexity or entropy and energy, which is some sort of a error or accuracy term as well. So this is one direction that one can take it. Actually, we did this a long time ago, calculating learning curves or this type of trade-offs for very complicated models or very simple models. But this is again detailed, and you can take it to many other places. One of them was this notion of the VC dimension. I don't know. I guess all of them are not. If somebody can bring me a black and blue, maybe. So the VC dimension is a very important combinatorial notion. So we saw, for example, that if there is a finite dimension to my class, in the what we call topological or metric sense, such that I can cover it with spheres of size epsilon, such that the number of spheres doesn't grow like more than 1 over epsilon to the d, then I'm fine. Then I can learn. The BIS dimension is a particular combinatorial dimension which helps us essentially characterize learning without the need to really cover it with spheres or things like this. And just short recall, so we defined a function which we called pi h of n, which was essentially the growth function of the class. So all these the growth function of the class. And this pi h of n was essentially what we said is the number of possible shattering. So how can I shatter a sample of size n? Means that can I label it with my class in all the possible 2 to the n configurations, or all possible 2 to the n labels. If I can do this, I said I can shatter, the class age shatters the sample, shatters with A. So it's actually, in some sense, it means that I can really isolate every one of the 2 to the n possible labeling by some hypothesis in my class. Usually many hypotheses in my class. Yes. So this is some function so it's the maximal, it's the number of possible, maximum number of possible, maximum over all samples, yeah, of size n, of possible labeling. Or if you really want to be more formal, it's the cardinality of this set, age of xr1 to age of xn. So it's just age belongs to age, and this is what we for a given sample, and then I maximize it over all samples, xn or sn. The cardinality of this set. Okay, and this is what I call the growth function. Sometimes it's called it's maximum over all samples. Or actually, if there exists a sample which I can shatter, then this will be n, 2 to the n. So essentially, what we said about this last time, this is either 2 to the n if there exists a maximum number for which this is 2 to the n, we call it d. It's 2 to the n as long as n is less or equal than some number that we call the VC dimension. If there exists a finite number for which this is true, and beyond that, it's bounded. Actually, it's true also for that. It's bounded by this funny combinatorial sum. Sum of I is in general bounded n over I, which we call the phi of n and d. And I convince you, I hope, that this is less than E n over d to the d. Okay, so this is what we showed last time. So this is nice because it means that up to this VC dimension, which is the maximum number for which this is, there is a full shattering. I can't find a sample, even one sample for which I can shatter, which means completely label in all the possible ways with my class. Then this goes exponentially up to some point, and then at some point it's bounded by a polynomial of n. And this polynomial is n to the d. If you actually check this, you can see that this bound is true also for n less than d. So it's always true. And then there is a celebrated famous VC theorem, which actually gives a bound on precisely this, on the uniform convergence in terms of the VC, in terms of the growth function. So the theorem of VC, which I just want to quote here, I'm not going to try to prove it. It's a little tricky, but it's something I wanted to take out of the idea of the proof. So essentially, the theorem, this is the Vatnik-Cheverenkis VC 71, is that what? Is that this probability over the samples for any distribution, that exactly what I wrote before, the supremum over h to the age of this EP age minus ES age is greater than epsilon, is bounded by some factor 4 pi age of 2n. So the complexity term, what I call the complexity term here, is actually replaced by this, multiplied by e to the minus, I think it's 4n epsilon square. No, it's just n epsilon square over 8. All these factors are quite loose. I mean, improve them in many ways. So this is, so you see, this is the Vapnik theorem and Yankees theorem. So essentially, it's telling us a condition from uniform convergence. This is always true. So I can, in some sense, find a bound, whether H is finite or infinite, doesn't matter. I can find a uniform convergence bound, which means a bound on the maximum, the supremum of the distance between these two curves, the blue and the red curves. So this will not be greater than epsilon. The probability this is greater than epsilon is bounded by this product. And you see again that this product has exactly the form that we want. It's a complexity function, which in this case is the growth function of the class at 2n. By the way, by 2n, so just if you look at the proof, you'll see that essentially what Vapnik and Chovanekis did is they bounded the fluctuation between two independent samples. So instead of bounding it the distance to the average to one sample, they took two samples, each of size n, and bounded the difference in the training error of these two samples. And then they showed by the triangular inequality that if they can bound the difference in two independent samples, then it also bounds the difference to the average. And so this is where the 2n comes from. Just remember this, there's a two-sample trick here. Two samples. And that's where it comes from, but if you don't understand, that's just if you ask yourself, where is this 2 coming from? It's not really very important. It's shifting the bound a little bit. So this is a little bit more complex, but anyway, in some sense this is better because 2n, if n is greater than d, 2n is certainly greater than d. And now we know if the class has a finite VC dimension, this is, we can bound it. So this is bounded by this term for 2en over d to the d times e to the minus n epsilon square over 8. So this is simply using the bound that we have on the growth function, which we call the Sauer's lemma. Okay? So you see the idea again is, okay, this is less than this. This is what I show, more or less. And I simply put the bound here. And of course, what we want is this to be smaller than delta. This is the condition for generalization, for high confidence. Okay, again, so this is the main trick. And this is the celebrated result of Vapnik and Chovanekis. Because this, of course, so again, I can put everything in the exponent and get a condition. So you see, this grows polynomially with n. This grows logarithmically if I put it in the exponent. If I put it in the exponent like I did here, this function will be d log n times some constant. D log n log n over d if you want. I don't care about log of e or things like this. Okay, so it will grow only logarithmically. This grows polynomially, and this grows exponentially with n. Or if you want in the exponent, this grows logarithmically with n, and this grows this decreases linearly with n, and therefore I can learn. So I can make it as small as I want. This is the idea. Okay, so what is the bound that we actually get from it? So if we just rearrange these terms, we get this, so the bound, which again looks very similar to the things that we saw already. So this will eventually give us that epsilon is bounded by the square root, again, where the square root comes from the fact that I have n epsilon square here. And again, the n epsilon square, I want only if you remember, comes from the central limit theorem. Epsilon is the deviation between the sample mean and the mean, which appears in the exponent of the Gaussian, and 1 over n is the variance. So it's x minus mu square over sigma square gives me n epsilon square, up to some constant again. I don't care about the constant. So again, if you want to write it exactly, it's 8 over n, so it goes like 1 over square root of n, times some logarithmic correction, which has this form, d log en 2en over d, 2En over D. Yeah. So this simply comes from this bound. And plus log 4 of the delta if you really want to. Something which is only logarithmic in 1 over delta. Okay, so this is the VC bound, where D here is the VC dimension. So whenever we have a finite VC dimension, we can bound the error. We can bound the difference. So essentially, what we know is that the generalization error of H is bounded by the training error plus this constant. Whatever. Yeah, this 1 over n d. Which actually I usually like to get the d over. This is the important part. This is usually you can completely forget it because it's so weakly dependent on delta. With delta to be 1 over a million, this is just a constant, and that's it. So this is the main part is d over n in some logarithmic correction. dvc log 2en over n. So there's a logarithmic term here which depends on n, but it's a weak dependence, which some people believe we can actually get rid of one way or another, but it's not really important. Okay, so now you see that if I do ERM, what is ERM? Empirical rationalization. If I minimize the training error, I get that the generalization error cannot be too large. It's bounded by this plus this correction. So if n is large enough, I can make the generalization error as close to the training error as I want. Oh, okay? Yes.
So when the VC dimension is not finite, you still have that bound. So why can't you?
So if it's not finite, this is exponential in n, which means that the logarithm has to be linear in n, and then these two terms will not win this. Or you have a linear term competing with a linear term, and you don't know that you can make it as small as you want.
Is that uniform convergence?
Yeah, this is precisely uniform convergence. So if you don't have a VC dimension, a finite VC dimension, this in principle grows exponentially with n, and actually you can really prove a lower bound. That if you have an infinite VC dimension, you cannot learn. I mean, you cannot generalize. So sometimes if this is 2 to the n or 2 to the 2n, doesn't matter, the log of this will not be smaller than minus n epsilon squared in large n, which means that there's no way you can make it smaller than any delta that you want. Okay? So the fact that you have finite VC dimension, if you have infinite VC dimension, did you see a class with infinite VC dimension? All of you? No. You showed them the sign, or? Okay. So there are classes. I just want to emphasize again, the VC dimension is not the number of parameters of my class, although it seems like your right intuition. It's not the number of parameters, it's something else. And just to see this, you have this example that you have to see yourself in the exercise of a class with one parameter, sine of omega x, the sine of sinus of omega x, and this is a binary classification of. But since the frequency is unbounded, I can make it, the VC dimension is unbounded as well. I can shutter samples of any size that I want, simply by taking the high enough frequency. This is, of course, related to the fact that functions that are not band limited in the frequency sense are hard to approximate. That's precisely the same statement.
Why?
Yeah.
Why in this case there is no width to the tube that you mentioned? Why EPH is not bigger than?
Because I have a bound on the supremum. Okay, so the supremum is the maximum distance between these two curves. It's the maximum width of the tube. So if I have a bound on the supremum, then I know that the probability that any H will be larger further away than epsilon. These are these two curves, the blue and the red curves. Okay, so this is telling you they are not further away than epsilon anywhere.
But in the inequality there, you're losing the absolute value.
Yeah, okay, that's no value. You're right. I mean, so it's one-sided. I really don't care if my generalization error is really smaller than the training error. This is good. I care that just that it's not much larger than training error. So I usually want a bound on one side. This is really what I care about. I want this to be as small as possible. Okay, when I put the absolute value, it's a two-sided bound. Right. But since you really want to minimize the generalization error, but you actually minimize the training error, so you just want to guarantee that generalization error is not too large. This is good enough. Okay, so it's really a one-sided bound which I care about. If epsilon p is much smaller than epsilon s, than es, I'm okay. I want epsilon p to be small. Okay, so this is why I got rid of the. So you're right. In some sense, you can gain a factor of 2 in the bound somewhere because I'm actually interested in only one-sided bound. So the whole thing is slightly. I don't need the 2 integrals of the tails of the Gaussian, only one of them. Okay, so this is really nice, and in some sense, this is the nature of all the bounds that we saw so far. If the complexity is finite, for example, the VC dimension is finite, then I can learn eventually, and I will begin to learn when my sample size is much larger than the VC dimension. So, for example, for perceptrons, what is the VC dimension? No, it depends on the dimension of the input. D or D plus 1, okay. It depends on exactly how you define the perceptron. With offset or without offset, but essentially it's D plus 1, let's say, the dimension of the input. So whenever the sample size is greater than the dimension, you begin to generalize, which means I cannot chatter my class. I cannot chatter my class. It means that some of the labels are going to be dependent, are going to be predictable from a small sample, and eventually this leads to this idea of support vectors. So essentially, I need to give you only very few points, and all the other labels will be generated by them. And that's also tell you how to. So you saw some examples. I hope it's really important that you do the exercise as good as you can, because this is important to understand how it works in practice. So for example, rectangles have this dimension of how much? Rectangle in the plane? 4. So 4 points is really the way, it's the maximum you can shatter. Okay? And therefore, you're going to start generalizing after 4 points. You can think also about it. In this case, also the number of parameters, because if you think about it as the 2 points on the diagonal of the rectangle. xy, x1, y1, x2, y2. So in this case, VC dimension is the dimension, the dimension, the number of parameters. But in other cases, like the sine wave or whatever, it can be very different from the number of parameters. So what happens with this single parameter? I mean, this single parameter can be very, very large. And we'll see that essentially what matters here is not really the number of parameters. Then I can reparameterize my class in many, many possible ways, but really the description length. How many bits are needed to specify that? And for omega to be very large, I need many bits. And we'll see this in a minute. What does this mean? Okay, so before I go on, I want to mention another type of bound, which I just want you to know the existence of such a bound. It's called the Pak-Bayes bound, which I actually find very, very useful in practice. Pak-Bayes. So this is a relatively new bound. It's due to David McAllister. I think this is how I write his name. I always make mistakes here. And it's around 99. But the theorem was. So David is really a guy of, I think he's younger than me, but more or less my age. And this is really a very, also a good friend, but was at Bell Labs at the time when he proved it. It's essentially some sort of an extension of the Occam's razor principle. So in the Occam razor, we actually saw that if the algorithm, not even the hypothesis class, is generating hypotheses which can be described by a small number of bits. So they are short in the sense that they have short description. And if this number of bits does not grow more than grow sublinearly with the sample size, then we can generalize. This was actually a very, very interesting insight, because I really didn't tell you anything about the class. I told you something about the algorithm, and maybe I generated from infinite classes. As long as the algorithm is short for all the hypotheses, as a function of the sample size, then I'm fine. So this actually has this combination of Pak base, which looks like a contradiction in terms. I mean, base, if you should all know by now, is a method that is based on distributions over my instances. And not only that, it's based on priors over my parametric spaces. Okay? So I need a prior. And Pak usually tries to assume exactly the opposite, that I am independent of the distribution and certainly don't have any prior or known prior distribution over my hypothesis class. So, but David said, okay, look, if you look at the Occam-Razor principle, and actually in a specific exercise that Noga gave you, you actually had a bound if you know the probability of generating the hypothesis, which is really very close already to the Occam-Razor. Some people even call it Occam-Razor. So it's so now what we want to assume is that we have some prior, Q of H, some prior over H. What does it mean? So before learning, there's a distribution over the hypothesis class, which says how likely or what is the probability that this prior before learning, let's call it pre-learning, will generate an hypothesis from a class. It can be uniform. So the entropy of Q, if it's uniform, will be simply the log of cardinality of H. If it's not uniform, let's say it's an infinite class, so it may be a Gaussian, or it may be something which has some structure. So this is the prior. So this is what makes it base-like. That's where the base came from. And essentially, if you have a prior, and then after learning, and actually I don't even have to specify if I learn it from IID samples or if I learn it using any tricks that I know or don't. After learning, you have a posterior. After learning from the samples Sn, but it may or may not be one sample, or may not be independent IID sample. I don't care. After learning, there is a posterior distribution, P of H, which I'm going to call. Actually, I really want to be careful here. This is, let me know this, the prior by P and the posterior by Q. Just it's always very confusing. QH so QH is the posterior. If you look at, there are different places to look, and they all use different notations just to confuse you. But if you look, for example, at Shai's, the Shai's book, Shai Ben David and Shai Shalev, or whatever, on learning, they have a nice section at the end on the Pak basin, which is very short and good enough for me. So, so this is the posterior. So after learning, the prior moves to the posterior due to the learning. So in some sense, what I mean here is that after I saw the examples, I selected there's only a small subset or some different distribution. So this is posterior, this post-learning distribution. And I really don't want to say anything about how I learn. So for example, one way that I worked on long time ago, and many others, is what we call the Gibbs type of learning. Gibbs type of learning tells you have a training error. So for every example, every hypothesis in your class, the probability of choosing it is e to the minus some beta e, the training error, which is a Gibbs type of distribution, for those of you who know what it is. And so essentially telling you, it's not necessarily ERM, it's some sort of a soft ERM. The probability of choosing any one of the edges is just exponential in the error, okay? With some beta. When beta goes to infinity, it will be ERM. And for beta, finite beta, it will be some distribution over the class. So this can be the posterior. And this gives you some sort of statistical physics of learning. I mean, one way of thinking about it. You can actually do whatever trick you have to generate a posterior. So what the Pak-based bound is telling us, so this is a theorem. This is the theorem of McAllister, which has all sorts of refinements and variations later on by many other people. So for all Q, for all possible priors, this is what makes it Pak-like. I mean, so so remember, there is in Pak there was only a for all about the distribution of the samples themselves. Here, I also assume a distribution over the hypothesis. It's an entirely different type of assumption. So for all for all agent P, whatever P, the sample, but actually in its cleaner way, I don't need, this is P. But I don't want to tell you anything about P, because I don't want to tell you how I learn. I don't need to tell you anything about how I learn. I just tell you that there is somebody whispered to me a posterior distribution. I guessed it, okay, based on something. So for all age of A's, epsilon and delta greater than 0, we have a bound. This looks very much like this. EP of age, oh, okay, the EP of Q, let's call it. So I need to define something. Yeah.
For all the priors or the posterior?
For all the priors, I'm sorry. For all priors. For all priors. So let's define the something which I want to call EP of Q. So EP of Q is going to be the expectation over all age that are generated from Q. Okay? Of what? Of what we call EP of H. Okay, so this is just an average generalization error over my posterior. Okay? And the same ES, it's a very natural thing. The ES of Q will be the average over all age in Q, the sample from Q, of my training error. Okay, so Sn here is a sample, but it's a training error. Okay? So essentially, what this is telling us that EP of Q, very similar to what I had here, is bounded by ES of Q. So this is the training error, this generalization error. Essentially, I didn't tell you too much about the training error, but assume that there is a sample and so on. Size n, plus something which looks very, very similar to the VC bound. So it's 2 over, it's actually simpler than the VC bound. So it looks like the D between the posterior to prior. Again, this famous scale divergence, plus some logarithmic dependent log n over delta divided by 2n minus 1. So this is called the Pak base. This is the Pak base bound. Yeah, I can even, so essentially again, telling you that the generalization error over my posterior is not going to be too far from the training error over my posterior. And what replaces the complexity term, for example, this term here, so is the KL divergence between the posterior and the prior. So this is nice. Right? It's nice because I can plug essentially any algorithm here. I mean, anything that generates posterior over my hypothesis by some sort of selection. For example, if I do ERM, in the realizable case, the posterior will be exactly the size. It will be uniform over the what we call the version space. I mean, all the consistent hypothesis is my sample. So this is one sort of posterior. So ERM is a special case. Can do Gibbs. I can do many other things. Yes. No, because this is what you're essentially going to do. I mean, so you're going to learn by sampling the posterior. I give you a posterior, let's say Gibbs distribution over my all hypothesis, and you sample one of them, and this is what I'm going to give you. Well, you're right, actually, it's some sort of an average error. So in order to do this, it's actually one of the things that come out of it is that it's actually better to give you some sort of an average over hypothesis in my class, which may actually be outside of my class. So for example, instead of learning one rectangle, you give a mixture of rectangles and average over them. This is a better class in terms of generalization than just one rectangle. But you're right. So this can be also what we call improper learning, which means actually giving you something outside of my class. But in general, what I'm telling you here, if you just sample at random from the posterior distribution, if the posterior is sufficiently sharp, then this is sufficiently unique. But if it's not sufficiently sharp, then sample one of it on average, in terms of average over the posterior, your error is not going to be too bad. Okay? But you're absolutely right. I mean, there's a question here. What is the practical meaning of this? It's an average over the posterior. So in order to really do it, I have to sample a few times and then take the best or average or do something like this. Okay, so this is, again, something I want you to understand. It's not very hard to prove. It just takes us 1 hour. And I really recommend this short section in Shai's book. It's very simple there. 1 page. This book. The book is called, that's why I took it with me, Understanding Machine Learning. It's very nice. You can actually find it online as well. You have to buy it. And it's essentially nice. This is the IML course plus many extensions. It's covered. It's a very nice book. I really recommend it. So in the last section, some of the last sections here, there's a short chapter on PAC-based, and this is where it comes. But you see that essentially, so why is it PAC? It's PAC-like in the sense that it's true for all priors. I don't really care about the prior. But so find the prior for which this bound is the best in some sense. And this is one way of using it. I mean, okay, so think about an algorithm which will minimize this DKL. All right, so this is essentially the end of this section. And I want to very quickly talk about something very important in somewhat, I have 2 minutes. Just state a question. So this is something which is a full chapter in the course, which we should give it a full lecture, but I don't have a full lecture. But it's called model order selection. Okay, so model order selection is essentially the problem that you encountered already several times in the course. First time, let's say you do a regression. And you have to choose which curve is the best. I mean, you have data, and you need to is the linear curve better than constant, or quadratic curve better than linear, or maybe high-order polynomial? Where do you stop? So where do you stop increasing the complexity of your class? So the assumption is that actually you have many classes. You also saw it in clustering, for example, in the k-means. I mean, how many clusters? It's the same type of question. I mean, obviously, one cluster is not very informative. A cluster for every point is too much. So something in between should give me the best possible model. How do you choose? So actually, I didn't really talk about clustering in terms of generalization, but you can all think about it. It's not very difficult. What I mean by generalization is, again, how well your clusters characterize points which are not in your data. Data. So in some sense, we have a hierarchy of we usually like to think about hierarchy of hypothesis classes, which can be more and more complicated. This is what we call nested classes, like polynomials. Polynomial first degree or 0 degree, a special case of polynomial first degree, which is a special case of polynomial second degree, and so on and so forth. And there are clusters, 2 clusters, a special case of 3 clusters, which is a special case of 4 clusters, and so on. So these are all nested classes. They don't have to be nested, but it's easier if they're nested. So if you have hierarchy like this, up to HK, this actually can go forever, more and more complicated classes. So for example, in the Occam algorithm, if I increase the description length, I actually allow myself to have more and more complicated classes. So how do you choose? Again, can I use those generalization bounds, this type of bounds, for example, the VC bound, to select the best possible class? So what would you do? What is the intuition? I mean, let's say I have a bound like this for every class. Every class, let's say, has a different VC dimension. Okay? So polynomials, for example, the VC dimension is more or less the number of coefficients of the polynomial, and so on. So it can be, how do I choose? So what do I really want to do? What do I really want to minimize? Again, I want to minimize the generalization error. Yeah. This is my goal, not the training error. The training error is the mean, is what I have, but the generalization is what I care about. Shape, generalization error. So I want to minimize this. So what would you do?
Take the first one.
So simply minimize both of them. Minimize the training error and the term and the bound over all the classes. Okay, so this is really very intuitive. I want to minimize. Now I have many possible bounds. Each class will actually give me a different training error because it may fit the data better if I have more and more complicated classes. But I care about this, not about this. So I really want to take into account the bound and minimize the sum of the training error plus the bound. Okay, and this is a very simple idea, which Vapnik called the structural enriched minimization, or SRM. Structural risk minimization. Minimization. Always forget letters. Or SRM. So the ERM was empirical risk minimization for a given class. SRM is now do empirical risk minimization over many classes, but select the one which will minimize the bound. So I have two terms here. I have the training error, and I have the complexity type term, which is going to increase with the dimension. Okay, so if you do this, for example, for polynomial regression, you'll see that usually you get reasonable bounds. I mean, actually, they are not good, very good. So they're actually, in practice, this is not such a great idea. In theory, it's very good. It can prove that for a large n, this will always converge to the correct or the best model. But the question is, how does it behave for small n or for finite n is tricky. Because those bounds are not very tight in general. So the idea is really, okay, now I look at the error as this ES plus bound as a function of k, where k, let's say, is the dimension of my class. So the assumption for given the sample, given Sn, there's going to be some function which will look like this. Maybe there's a minimum here. So take the one which has the minimum bound. So again, it's not enough that this is minimum. This also has to be small. Some of them has to be small. So take the minimum. So it's the argmin of the bound of ES plus, let's say, this bound H whatever complexity term plus the bound. Let's call it complexity bound. Minimize this over all the k, over all k, where k is the index. K is the index of this nested k from 1 to whatever infinity. As far as I care, all of them. You're right. So I do ERM. I want to minimize the training generalization error. So I want eventually an hypothesis which minimizes generalization error. I do it by minimizing the sum. So I find an hypothesis which for each class I minimize the error. But then I look at the sum of the error in the class, the best error in the class, plus the complexity term, which doesn't depend on age in general. And so this sum will have some sort of a trade-off. I mean, it's a trade-off between how well I fit the hypothesis, which is the accuracy. But again, in the polynomial regression case, it's how well I fit the data versus how complex is my class. And I take the one which has the best one. So this is called SRM. Let me stop here. So there are two other topics which are related to this. One of them is called cross-validation, which I just want to mention. And the other one is related to compression, which is usually called minimum description length. But in order to actually understand why essentially what I'm telling you here, this is some sort of a description, a coding length statement. It's again related to Occam. The one which allows the shortest description of the data is the better model. This has a general philosophical principle that is known as MDL, or minimum description length. In order to understand this, I need to talk about compression for a while. And this is what I'm going to do right after and then there's the MDL, and this is more or less will close the course at this point. Okay, so there are two more arguments here that has to follow the model order selection. One of them is simple to understand, and the other one is actually very practical, cross-validation, and the other one is MDL, which is also very interesting. So don't go away. אנחנו בוחרים את P. עכשיו ניתן איזשהו אלגוריתם. האלגוריתם הזה משנה את הפרט, את הסיבוב שלו. כמו שראינו הרבה פעמים. ראית דאטה, פסטיר משתנה. פסטיר, אתה יכול לדעת עליהם פסטיר דרכים. למשל, כמו שאנחנו נתתי בדוגמה אחת, אמרתי את זה קצת מהר, הפסטיר זה אקספוננציאלי בספייה. זה נקרא גיט, אוקיי? So for example, דרך אחת זה פסטיר, סליחה, פסטיר כזה, זה הפריור כפול אי במינוס בטא תשגיח. טרנינג יחד. בסדר? נקרא פה, נקרא לזה ESN.
כמה שקלות כמה שקלות...
ואני אתן למד את זה, זה כאן איזה משהו תלוי בזה. בסדר? זה נקרא גיט. בסדר? אז שים לב שבמקרה הזה, הלוג פסטריו טו פריור, במקרה הזה, ה-DKL הזה, אז הלוג Q over P, זה פשוט הלוג של הדבר הזה מרכזי. זה יהיה הלוג של E במינוס בטא ES מרכזי. אני יכול לכתוב כמינוס בטא ES, ESH, מינוס לוג Z. זה זה יכול להגיד זה. אז אני אמצא את זה כאן, ה-DKL, ה-DQP, יהיה מינוס בטא האנרגיה המוצא, Q, נכון? כי זה מוצר Q, זה משהו רגע.
כן,
מוצר Q, פחות זה שלא תלוי ב-Q, אז וזה יהיה הגודל שאותו אני נותן על זה, זה הקומפלקסיטי שלי. מה בעצם הוא אומר? זה לא מספיק למזער את צביעת האימון, צריך לקחת חשבון את האורגניזציה, את ה-free energy. זה נקומפלקסיטי של... זה בעצם יהיה הולך להיות העיקר. כלומר, למזער את זה זה ל-ERM. זה ERM ממוצע על הכלי. אבל למזער את זה הולך להיות טריקי, זה הולך להכיל את זה. בעצם מה שקורה כאן זה מאוד יפה, לכן אני אוהב את זה. הוא מחליף, ה-D הזה במקרה הספציפי הזה של גיט, זה הגיט, נקרא דיפ לרנינג. דיפ לרנינג או סטטיסטיקה מכנית, איך שאתה קורא לזה. במקרה הזה של סוג של אלגוריתם, זאת אומרת, אני יכול לממש את זה בעזרת סטוקסטי גרדינג דיסטנס, למשל, או כל מיני טריקים כאלה. אני לי כאילו בתוך הקלאס שלי, ואז אני מגיע להיפותזה שההסתברות שלה היא אקספוננציאלית בשגיאה. כמה שגיאה יותר קטנה היא תהיה יותר סבירה. אבל לאו דווקא אפס, או בטח שפי. אתה רואה שיש כאן איבר, זה פנלטי כזה, סוג של... אנחנו רואים שהשגיאה, הדבר הזה שנותן לו קומפלקסיטי, זה כמו זה ועוד תיקון, אבל התיקון הוא הפרי אנרג'. זה אנחנו רואים פרי אנרג'.
אבל...
סוג של פרי אנרג'.
אבל נגיד פה אנחנו לוקחים כאילו פעמיים לחשבון את האירור...
לא, אני כרגיל רוצה להקטין את זה.
נכון, אבל יש לך, ואז אמרת שזה שווה
אני רואה שבמקרה הזה יהיה כאן שורש של האירור הזה. יש כאן עוד שורש של האירור, של האירור המוצר. אבל כל הגודל הזה יחד מתנהג כמו אנטרופיה פלוס שגיאה פלוס אנרגיה, זוג של פרי אנרגיה. אבל אתה רואה שהלוג זה עושה כאן את זה. זה בדיוק מה שיכניס פה משהו שהוא לא סתם השגיאה.
כן. כאילו את הקומפלקסיטי שלנו. אבל ואין לנו בעיה עם זה שאנחנו בעצם לוקחים, צריכים לקחת באמת איזה average, כאילו...
אני יכול לראות לך אפליקציה שיש לי אישית 10 מאמרים על שימושים של פאק בייס וכל מיני בעיות. בדרך כלל בעיות או בקלאסטרים או בעיות שהן יותר מסובכות או בעיות ב-MDP, POMDP, כל אחד שהדינמית הזכרתי את המון. שם אנחנו מאוד יודעים שאני פאק בייס מאוד נוח. זה סוג של, להקטין את ה-DKL הזה, זה דבר שאני יכול באופן פרקטי לעשות את זה. אני אראה לכם בקורס אחר אולי איך עושים את זה בפועל על מודלים דינמיים. אבל זה אומר לך, אוקיי, אם זה קטן, תבחר את הפריור והפוסטריור ככה שזה יהיה קטן, אתה יודע שאתה לא יותר מדי גרוע.
כאילו, אני לוקח, אבל המינימום הוא על המינימום של ההיפותזה שנותן את המינימום, נכון?
אני אבחר את המינימום של זה, שני דברים ביחד, אבל אני אומר כאן, בואו נקרא על האלגוריתם עצמו. בואו נראה איזה אלגוריתם, איזה סוג של מודל אני רוצה להציג בנתונים שלי. זה ישפיע מיד על הגורם הזה.
אני קודם צריך לבחור מודל.
במודל הזה אתה מגדיל באיזושהי צורה, למשל נגיד, אתה יכול להגיד בכל צורה אחרת. תן לי פוסטריור, תגיד לי מה הפוסטריור, איפה אתה מוצא את ההיפותזה שאתה פיתח חי. אחרי שאתה אומר לי את זה, אז אני אגיד לך אם זה טוב או לא טוב. רק בתוך הסתכלות על כמה הקטנת את הדיקים הזה. מאוד פשוט.
אבל כאילו, זה לא יותר בעייתי מאשר שיש לך מודל, גם פריור, כאילו, וגם כאילו, לדעת שאתה פוסטריור.
פריור תמיד יש לך, גם אתה לא יודע. כלומר, כל אלגוריתם יש לו איזושהי העדפה התחלתית למשהו. בדרך כלל זה נובע משיקולים חישוביים. למה קל למצוא, למה פשוט למצוא. בדרך כלל סוג של פריור של אלגוריתם, זאת אומרת, אין לי פריור, ואני לא בסיינן לא אין פריור, ואתה נותן לי אלגוריתם, ואני רואה איך אתה מאתחל אותו. ואיך אתה בוחר את ההתחלה שלך בעצם. ותחול את זה סוג של פריור על ההיפותזה.
למה אתה קורא לזה after learning? שוב מהפריור?
הפוסטריור הוא after learning.
כן, אבל והפריור?
פריור הוא לפני נראה, פריור. פריור זה משהו של אלגוריתם.
הוא לא משתנה בלמידה.
לא, זה פשוט ה-Q, זה מתייחס ל-Q. זה כאן יש נקודה?
כן, הבנתי.
after learning הם גם פוסטריור. אז זה פשוט כתוב בסוף. כאן יש נקודה. אז זה after learning יש לך את זה. לא, הפריור הוא לפני הלמידה, תחשוב על זה כהתחול של האלגוריתם.
בעצם המשוואה הזאת קצת אומרת לי שאם כמה שבחרתי פריור יותר טוב, אני מצפה שיש שינוי כמה שיותר קטן,
אז אתה תהיה מצא יותר טוב. זה לא חוכמה, כן? אם הפריור שלך יודע כבר משהו על מה שאתה מחפש, תיקח את חשבון.
אם זה לא היה ככה...
אם אתה, נכון, בדיוק. הפריור אומר לפני שראית את הדאטה. אני רואה שאתה כבר יודע כל מיני דברים שאתה ראית את הדאטה.
רוב העדכונים הם רנדומיים, לא יודע, האלגוריתם שאנחנו ראינו, זה קיימינג, לא יודע, אתה בוחר כמה נקודות וזה הסנטרוידים הראשונים.
זה בסדר, זה פריור אחיד. אבל אם היית אומר לך שהסנטרוידים לא יוניפורמיים ביוניפורם, על הישן, אז היית מגדיר את זה פריור, גאוסי, היית עושה משהו. או נמצא לי מה, אני יודע, אתה רוצה לבנות איזה מודל יותר מסובך, נניח מודל דינמי כזה, יש פה אחת מהרשתות ה-BCI האלה שראיתם, MVP, כל מיני מודלים כאלה, שם ההתחול הוא כמה פחות אידיאלי. באיזה סט אתה בוחר את ההתחוליות הנפלטים שלך? למשל, באיזה ממים אתה בוחר את התצפיות להיות גאוסיות, למשל, באיזשהו סדר, או אתה בוחר את המרקוב להיות נפרק, או באיזשהו מרכיבים, כל הדברים האלה הם תחולים של פרייר. באיך אתה מאתחל אותו? בקיצור, בפרייר נכנס כל מה שהכנסת בין במבנה של מודל ובין בהתחול של הפרמטרים של המודל. כל המטה פרמטרים, כל הדברים האלה. אבל זה יכול להיות כלשהו. מה שאני אומר לך, המורכבות של המודל שלך בעצם נקבעת על ידי המרחק מן הפוסטריור לפרייר.
כמה הלמידה בעצם?
כמה שינית את הפרייר נתן ללמידה. זה אינסייט מאוד חשוב.
כאילו אני רוצה לא לשנות בעצם את הפרייר, נכון?
כן, אם לא תשנה את הפרייר, אתה יכול להיות הכי קרוב לפרייר שאתה יכול, אבל אתה ממש רוצה ללמוד משהו. אם אבל שינית הרבה את הפרייר, אז אתה צריך יותר דוגמאות.
אוקיי.
אתה צריך הרבה יותר דאטה.
אוקיי.
בסדר? אם זה מאוד גדול, אין לך נמצא.
אבל כאילו, הם לא חייבים להיות קשורים, הם לא קשורים, נכון?
הפרייר והפוסטריור?
לא, ה-DKL ו-N.
לא, לא קשורים. DKL זה תכונה, הפוסטריור באופן מעשי תלוי ב-N. נכון? כמו שאתה תגיד את זה.
כן.
הפוסטריור תלוי בטריינינג אירו, וזה תלוי כמובן בשגיאת האימון ב-N.
אוקיי.
אבל זה אפילו תהירה איך האלגוריתם משנה של המדגם. כלומר, האלגוריתם משנה את הפרייר, הופך אותו להתאגרות אחרת. הוא עושה את זה דרך הדוגמאות, דרך הדאטה. אתה כן תלוי במדגם, אבל לא עובדים ישיר. אני מחליט בולע את כל התלות של האלגוריתם בדאטה לתוך הפרט, לתוך הפסטריות. איך הוא משתנה? כן. אז ראיתי שאתה מחפש אותי בהקשר של הקובץ.
אז רציתי לשאול אם יש לך זמן או בשישי או יותר מאוחר היום.
אני פשוט שבוע נורא לחוץ, גם סוף לימודים וגם כל מיני הרבה מועמדים שסתובבים פה שכל אחד בהרצאה וראיון וכאלה. הזמן שלי מת היה מאוד מרוכז בשבועות. ביום שישי אני אהיה פה, ושאל רוצה לקרוא
אז זה יתקרב לזום לך במייל איזה שעה
משהו החל מ-10, בין 10 ל-12 אני בטוח יהיה ברצון.
להתקשר לך לפני שאני מגיע, לשלוח מייל או בנפיצ'ר ואז תעשי שעה.
כן. כן, אני אגיד את כך נראה שאף אחד לא יודע את הקשר. בטח לא יזדיק לשמוע את זה עוד פעם. כן. אני רוצה לחסום את כל החסם, זה מה שאני, זה אני רוצה לעשות קצת.
אבל למה לא כאילו יותר לנפט? ברגע שפה שהנגזרת מספיק נמוכה,
אני לא מסתכל פה על הנגזרת, אני רוצה באמת להקטין את השגיאה, לא מעניין את הנגזרת. להפך, מעניין אותי נקודה שבה אני לא יכול לשפר את זה. אתה באמת רוצה שגיאה קטנה. זה שהנגזרת, להפך, אם הנגזרת גדולה, תמשיך ללכת. אם אתה יכול עדיין להשתפר, אז תשתפר, כמה שאתה יכול.
כן, אז יכול להיות שזה עולה לי מן הסתם בדברים אחרים.
לא, בסדר, נכון. אז תעצור שזה מספיק טוב. לא חייב להגיע למינימום. תגיד לי מה השגיאה שאתה מוכן לסבור. זה טוב שם. מספיק טוב זה בדרך כלל בסדר. מספיק טוב אנחנו רואים להפוך את זה, בדרך כלל אנשים באמת אומרים יש לך איזה דרך. השגיאה יורדת, אבל זה מתיישב. זה מיישר, עושה את הדרך למינימום. אתה צודק, שבדרך כלל מה שאנשים עושים זה נותנים על איך השגיאה משתפרת, אתה אומר שזה לא משתפרת, צריך לעצור. זה הקריטריון שאנשים משתמשים בו ככה כלל האצבע, שכולם אומרים, תסתכל איך השגיאה יורדת, כשאתה מפסיקה להשתפר, אז כנראה זה זה, אבל היא יכולה להיות יותר גרועה לו. אם תמשיך לסבך את המודל, השגיאה תרד, זה לא אומר לך כמעט כלום, כי זה יכול להשתפר. אז זה באיזשהו מובן מפרמל קצת יותר טוב את הרעיון הזה של הברך. לאף מתכוון.
What does it say? The argmin of what?
So it's the argmin over all the hypothesis classes.
Right, no, underneath.
So this is H1, this is H2, this is H3, and this is H10, I don't know, and so on.
I just can't read what you wrote.
It's K, this K.
Oh, it's K, okay.
Or argmin over all K.
Okay.
K going from 1 to whatever the number of this is polynomial constant, polynomial first degree, second degree, so on. Things like that. The more complex your model, I denote it by this. You can think about it as a basic dimension count or something.
גם מה שיכול באמצע, איך אני יודע מה יסתכל שזה יעד? אני לא יכול לעשות, אם זה מאוד מאוד קטן, זה יקבל עבורים לא מאוד מאוד קטן, זה יקבל לא, אבל זה חלק החמישי, איך אני... הוא לא תלוי בזה. זה לא יהיה מאוד קטן.
Okay, so I'm going to butcher another topic. Okay, some people ask me again some good questions during the break. Again, about PAC-based. So again, the prior is usually something which is not explicitly given, but it's actually determined by the initialization process of the algorithm. For example, in the clustering problem, you selected randomly the initial clusters. But randomly is not, there's no random. There was some underlying distribution from which you selected the clusters, okay? So it was some sort of initialization. If it was not a uniform interval, it's not necessarily simple what I mean by random. Random, something I want you to take home from this class, I mean, random is not something you have to specify. I mean, what do you mean by random? random over uniform distribution over what, so on. So the initialization is usually in the prior, and the posterior is usually something which the algorithm generates, I mean, by using the data. So I gave here this example of the Gibbs learning. The posterior is the prior multiplied by an exponent over the training error. This is what we call Gibbs, normalized. And then you see that the KL divergence is simply the average error plus log z. And actually this log z is really the complexity term here. It's some sort of a free energy. This is really what's going to make sure that you are not too bad in terms. So by minimizing this DKL, you actually minimize some sort of free energy, which is really this, again, you see some sort of combination of the training error and how much log z is minimized. So in this case, it's minimizing this is really equivalent to penalizing over complicated posterior. So if the posterior is very different from the prior, what it means is in order to get a good bound, you need to minimize. Again, I want this to be smaller. To get a good bound, if this is large, you need much larger n. That's all it says. More data. So in general, if you want good models, you want to minimize this posterior prior KL divergence. And some of you may know that this is something we can take to many different places, like MDPs, POMDPs, clustering, many other algorithms. Okay. So I want to. Oh, I lost it completely. Okay. So I just want to say one word, and that, because I understand that Noga already described cross-validation to you. So cross-validation essentially is a way of estimating how bad are you in terms of generalization without really calculating the generalization error. So what I would like to do in principle is to take two samples, two independent samples, and make sure that if I find a model that is good for the one sample, is not too bad for the other sample. So this is called cross-validation. Validation. So essentially, what you take is you have your data, and you divide it into two pieces. One of them is randomly the set that you want to train your model on, and another one is a set of examples, which may, in the extreme case, be only one example. This is what we call leave one out. Leave one out means, okay, take all the data except 1 point. Of course, this can be too bad. I mean, 1 point. So what you do is average over this 1 point. So you take many times one out and see. So this is in order not to waste data, because you want a larger sample set. So you leave only one out. So leave one out is a special case of cross-validation. But in order to make sense of it, you really need to average over this example that you leave out. In other cases, if you have enough data, simply divide it into more or less equal pieces, train on one, and test on the other. So this is the idea of a training set and a test set. And actually, if you look at the way the bounds are constructed, if I know if the two samples are going to give me very close error, or very close model, then it's probably going to generalize well because of this trick of the two sample trick of Butnick you want. I mean, if the two sample error difference is small, then the generalization error is going to be good enough. And this, of course, something I have to prove, but the proof is very, very similar to the uniform convergence bound that you already know. So if two samples are close enough, then they're probably close to the true minimum. If the two samples are fluctuating a lot, I get one model here, and entirely different. I do clustering. Take my data divided into two. When I get one clusters here and another clusters here, which have absolutely no similarity, then you're probably overfitting. You're probably off. I mean, how will you choose? But if they agree, then you're okay. So cross-validation is a very intuitive thing, and it's really done in practice a lot. It's actually related to another notion which is called stability. Stability is essentially how much your output of the algorithm depends on small deviations, small fluctuations in the data. Let's say, so I don't want to do cross-validation because I don't have enough data. So I can take the data and then perturb it a little bit. How do I perturb it? Add some noise to the features, or do something like this, and then train again. If I see more or less the same result, then I'm okay. This is called the stability criterion. Ohad Shamir actually did his whole thesis on this, more or less on this question. I mean, and a stability criterion is really very. I believe it's actually the right thing to do, but the question is what type of noise against. It's a bit tricky, but you can think about a different sample as some sort of a noisy version of the first sample. It's really not a noisy version of the sample. It's another independent data. But how much you are sensitive to fluctuations in your data? So intuitively, if you're very sensitive to fluctuations in your data, then you're not. It's not good. And this is actually correct. I mean, so you can you can mimic cross-validation by essentially generate another sample by a noisy version of your current sample. And in some cases, it works well. Okay, so this is cross-validation. Two samples. Two samples, training plus testing, as it's usually called. You have to be very careful not to then retrain your model on the testing, because this may give you overfitting immediately. So you use the test and keep it as a test data. Don't touch it in terms of training affecting the algorithm. Okay, so the other approach that I want to describe briefly is called is actually a set of arguments which are based on information theory or based on compression, which are already. I mean, they're very close to the Occam's principle that we talked about, and I like usually to call them MDL, or minimum description data, length. Sometimes Bayesians actually have a very similar thing, which is called BIC, which is Bayes information criterion. It's actually there's a big fight in the literature between those who believe in MDL and those who believe in BIC. It's really a religious type of argument. Whether you want to pray this way or this way, it's the same God exactly. It's exactly the same principle. It's just whether you believe in priors or you don't believe in priors. I mean, whether you would like to cast this as some sort of a prior. These are two things which are very related to each other, and I want to state them in terms of what we call data compression. So this is a whole new topic in principle, but it's closely related to what we said so far. And it's actually the beginning of what should have been a set of at least 3 lectures on information theory. But I don't have 3 more lectures, unfortunately. I'm sure you're not going to come during the break to hear the rest of the story. So take another course if you can in information theory and or hear it somewhere else. Okay. Now, so what do we mean by data compression? So essentially, there's a very basic notion which we call source coding. And I'm very intuitively and briefly going to describe what we mean by this. So we have a distribution over some sample space. This is, again, as always in this course, there is some distribution which gives us data in some, and this is what we call source. And the source has a distribution which we at this point assume we know, okay? Now, the point is, now I'm giving you a long sample from this distribution. Okay, so I'm giving you actually x, what I call xn or sn, sampled from this p to the n of x. And so this is a sample. The source itself may also be very long. I mean, I can have inputs like documents. Documents are kind of this. So documents are, you can think about them as samples of characters, but they're really not samples of characters. They're samples of they're not even samples of words. I mean, they have structure, which is much more than that. But I can think about sources of things like documents in newspapers, or sources like images, or videos, or politicians, or whatever you want. Okay, I mean, so I can sample them from whatever. Now, so that can be very complicated things. Now, my idea is I want to describe to someone else that my data in the shortest possible way. So you can think about it as I want to put it on my disk and then read it later on. And I want to save disk space. This is very simple, very intuitive, everyone here. So I want to keep the data in the smallest possible, shortest possible way on the disk. think this is something everybody here should understand immediately. Or in the way that it was conceived, it was actually a problem of communication. I want to send somebody else my data, and I want to save. I mean, there was at the time of Shannon, it was the Second World War. People actually used Morse codes to to transmit information, and you really think about this this spy in Berlin who is transmitting a message and want to do it in the shortest possible way because long transmission will increase his chances of being captured. Okay. So this was really the problem that Shannon encountered at the time. I mean, how to save bits or the save transmission time. So what is the fundamental question here? The fundamental question here is so I want to take any x like this and assign a code word to it, something which I call C of x. And this code word, so this is code word. By the way, the word code is often used, especially now after you all saw or should see the movie about Turing. So there's a very big difference between code and cipher, or encryption. Code is simply a description, and you know, in our everyday life we completely confuse these things all the time. So code is, so I'm actually going to assign a code which is, without loss of generality, think about binary code at this point. So it's some sort of a string of bits. Okay? So I want to assign each instance or each x in my data a string of x which will characterize it. This is what I'll call a code. So this is a string. We all know what a string is. So this is an ordered sequence of bits. Okay? Now, so I want obviously I want a short description, so I want finite code. So what I mean by finite code, I want to assign to each of those code words there is something called the length. Let's call it L of x. So this is a length function. Length of the code. Length of the code in bits. How many bits are in each word? Okay? Very intuitive. Okay, so the length of the code is the size of this string. So a string is a sequence of bits. Size of it is the length of it. Okay? So, and this is something called length function. So in principle, I would like to encode my data in short way, which means give short code words. Okay. So I can give all of them the string 0. It would be very nice, very short. Actually, I could give them nothing at all. But so why is this not good enough? Because there is something else that should come with the code, and this is the ability to decode. Okay. So this is encoding it. So I want something which takes C of x and turns it back into x, which I call decoding. Okay? So of course, I want to be able to decode my data from the compressed version. You don't want to compress your data on the disk and then can't able to read it anymore because it's too compressed. As you want the simplest possible description, but not more. Not too simple. It's the same idea. Okay. So what should you do? So what is the condition that the code is decodable? Actually, usually we say uniquely decodable, which means that for every code word there will be unique x, which will get given. So it should be a one-to-one function in some sense. Okay. So I want the code to be uniquely decodable in the sense that this mapping from x to cx is one-to-one. I can decode it back, but I want to. So here I'm going to say something which is very. I need more time for this, but it should be very intuitive to you. So I want to decode it, but I want to decode it in a way which is. Sometimes I really want instantaneous decoding. Essentially, what I mean by code. So if you look at a sentence in a paper, let's say, you can actually break it into. You can parse it. You can put commas between the different words and know where each word ends and the other began. So this is actually called instantaneous decoding. So I should be able to run through my sequence of bits and say, okay, but I want to decode more than one word. So essentially, I want to talk about something which is called the extension of the code. So if I have a sequence x1, x2, and so on, xn, and I code this one by cx1, and then concatenate this one by cx2, and this one by cxn, this should be the code of the whole sequence. But it's another string, so this is concatenation of strings. Just put one sequence after the other. It's all bits. But you should be able, in a unique way, break this and what we call extended code, the code of a long sequence, into uniquely what we call parse it. Okay, so how do you do that? So the first intuition is very simple. You encode your data by building a tree. Okay, so let's, you don't see what I'm writing there anyway. So let's, I really hope to have at some point during my lifetime a better board here. Okay, let's see. It's not here, maybe in your building, somewhere. So you want to pass some what you call uniquely decodable codes is actually something which should allow me to take a long sequence of bits, whatever it is, and say, okay, this is the first word, the second word, this is the third word, and so on, and pass it. So I can take this C of xn, which is the concatenation of the sequence, and say, okay, this was actually C of x1, this is C of x3, and this is C of x4, and so on. Put these commas here is passing it. And one easy way of understanding how to pass things is to build, as I said, a tree, a binary tree. Let's say this is, so 0 is going to be here. So, and what I mean by this is that I drew a binary tree. So you all know what a binary tree is, I hope. This is a binary tree, and actually an exhausted tree. And I just put code words. This is going to be cx1. This is going to be cx2. This is going to be cx3, cx4, and so on, cx5. So there are 6 code words here. And I say that if my code words actually works on the tree, so x1 is encoded by 0. x2 is encoded by 1, 0, 0. Okay? x3 is encoded by 1, 0, 1. x4 is encoded by 1, 1, 0, 0, and so on. Okay? So any code word is essentially a walk from the root of the tree. It's called the root of the tree. It's actually the beginning of the root, not of the tree, but it's upside down. But it's and I go down until I get to a leaf, which is the end point, and this is my code word. Now, you can convince yourself, and it's not very hard to prove, that if my code word R passes on a tree, then it's uniquely decodable. Why is it uniquely decodable? Because, okay, you start here, you walk. You start with 0, 0, 1, 1. 0, okay. There's a comma here because after 0 there's nothing. And then 1, 1. Okay, 1, 1, 0, 1. 1, 1, 0, 1 will bring me here. Will bring me 1, 1, 0, 1. Will bring me here. Okay? So this is, I go to another leaf, I put a comma. And so on. I run forever, and then whenever I get a comma, I go back to the root. So an algorithm, a decoding that goes along a tree is a unique way of passing a long string. Okay? So a tree is a good code. If I could generate trees, it's a way of generating uniquely decodable codes. It's not the only way. I mean, if you think about the text in our language, so there are not two alphabet numbers, but not two alphabets, but 26 or 27 or whatever, including the punctuations. It can be more. But let's say 26 or 27 letters. This is not a tree code. A tree code has also a nice property which we call the prefix property. I mean, so no code word is a prefix of another code word. Why? Because there are no, the leaf's always at the end, so this cannot be a code word. 1, 0 is not a code word here, okay? Or 1, 1 is not a code word here. Okay, so any prefix of another code word is not a code word. So this is called prefix free. Or prefix, it can also be a suffix free, but normal language is not neither suffix nor prefix. I mean, you can have words that are prefix of other words, and you can have words that are suffix of other words. So usually what we do is we put blanks or separators. But this is a very expensive way of doing it. I can actually save a lot. But there's one way of parsing it uniquely. And as you know, actually all texts, even all Bibles, for example, have no commas. I mean, you just really have to read it without the spaces, which is much harder. Of course, not always unique. Okay, so the idea of this uniquely decodable code is actually a condition on the length function. So in this case, the length function is 1, 3, 3, 5, 5, 3. Okay, so there's a certain length to each code, and it turns out it's only the length really matter. I mean, there are many, many trees with the same length function, but in this case, it turns out that the property of unique decodability is a property only of the length function. This is actually a very nice statement, a very nice theorem, which tells you, okay, if you want to know if there is a uniquely decodable code with this particular length function, then the answer is if and only if there is a uniquely decodable code to this function, if and only if, so C of x is a uniquely decodable code. Okay, uniquely decodable code. You should write it full. Uniquely decodable code if and only if something which we call the Kraft inequality. This is something actually turns out to be very, very important. If and only if I'm talking about binary code now, the sum over all x's of 2 to the minus lx is not too large. Actually, less or equal than 1. Okay, so this is a very nice theorem, if you want. It's true for any uniquely decodable code. That if and only, so give me the length function of the code, and I'll tell you if there is a code like this. So why is this true? So you can convince yourself rather easily, but again, it's not entirely trivial, that for trees it's true. Why is it true for trees? So the idea is really to complete the tree, the full tree of the maximum length, maximum size, and then show that for the full tree, this sum will be exactly 1, but then if you shorten it, actually, you really bound the difference between the full tree and the small tree. And this is maybe Noga will say something about it, maybe not, I don't know. But essentially, for full trees, you should be able to convince yourself rather easily with some guidance that this is true. It's a little more tricky to show this is always true, but it's actually a very simple proof, which I'm not going to show you now, because there are some other things I want to show you. But believe me that this is true. So this is called the Kraft inequality. By the way, it's true for any sequence. For example, programs on your computer also avoid the Kraft inequality if there are different programs, if they are identifiable and so on. Okay, so this is important. Remember this. It's a very important lemma, if you want, for this particular subject. So you can see, okay, this is the answer to the question: can any code length work? No. If the codes are too short, this will be too large. If this is too short, this 2 to the minus L will be too large. So for example, you see that if I have 2 code words, this is the maximum I can do with 1 bit. Okay? Because then it will be half plus half. That's it. If I want more than 1 bit, if I want more than 2 code words, let's say 3 code words, I already need to go beyond 1 bit, which is obvious. So 3 code words here will be, let's say, this small subtree. So then it will be half plus quarter plus quarter. Okay, that's okay. And so on. So you see that if you want more code words, you need longer words. And as long as they obey this inequality, that the sum is not larger than 1, I'm fine. Okay, so this is a small exercise, which somehow between Noga and you, you'll have to see, at least for trees. Actually, I really like the general proof because it's so elegant. It's a bit surprising, but it's true always. Okay, remember this. Okay, so this is something called the Kraft-Macmillan inequality, because both of them proved it more or less independently. But So now we want to use it to get a very simple statement. Where should I do this? So I'll get rid of the bounds. So now, if this is true, if you take this as given, craft inequality, I'm going to show that there is a very nice bound on the code length, on the average code length, which actually is very simple to prove, which is sometimes called the first coding theorem, or the lossless coding theorem of Shannon. And this is all we need right now. So let's first give you the intuition as always. Then we'll state the theorem. So we had P of X. The question is, how is the code length related to the distribution of my data? So in some sense, intuitively, maybe you already feel that if the distribution, somehow it should be related to this, because it should be related to something which we actually call the entropy, and this is really the nice thing about it. But so given this, the expected code length over P is what? The expectation over P of L of X, or just in the finite case, let's write it like this. In the discrete case, which is all we care about right now, this is the expected code length, okay? So this is the expected code length. Remember, L was a function, a length function of a code, okay? So I want to see what is the minimal expected length. Is it bounded by something? So let's define just an auxiliary distribution. I call it Q, which is 2 to the minus L of X over the sum, normalized. Okay? Those of you, some sort of an exponential distribution, it really reminds you. But so the normalization is precisely this quantity that Kraft wanted to be less than 1. Okay? So this Q is a distribution. Okay? This is greater than or equal to 0. So if it's a distribution, I can actually look at what? I want to see how is this distribution different from P. It looks like, why should I do this? But we'll see immediately why should I do this. So let's look. We know that D, PQ, the famous D, is first of all greater than 0. Okay? The famous DKL. So let's look at it for a second. What is it? So it's the expected over P of the log of P over Q. Okay, just to remind those of you what I mean by that, of course, you should know. And then I'll plug my Q here. So I see that this is sum over X of Px log Px. What is this? Minus sum over X of Px log Qx. Okay, this is of course trivial. But log Qx is this, so this is going to be, it's minus the entropy, but let's still write it sum over X log Px. And this is what? So I take the first term is minus 2 to the minus, so let's take log 2 here to make life a little easier, just simpler. Okay, so log of 2 to the minus L, what is it? It's minus L. So it's going to be minus sum over X, Px Lx. This is exactly the expected length. Okay, now what did I miss? The minus, it's actually plus, because the minus minus, plus the log of this sum. Okay? Now this is nothing more than just writing the KL between these two distributions. But what do I know now? So I know that the whole thing is greater than 0. So what I get from this is that the code length, the average code length, with respect to P, is greater than minus the sum over x of px log px plus this Kraft term. But since this is this, if I assume unique decodability, this is less than 1. Or if this is less than 1, this number is negative. I'm sorry, something is wrong with the sign. There's a minus here. There's a minus here. This one is minus. The sign is wrong. This is minus. Yeah, that's what it should be. No, it's all right. It's all right. Everything is okay. So this is a negative number. No, it should be the entropy. Something is, this should be. No. Here. All pluses. Okay, fine. This is one of those things that you remember, but usually remember wrong. Okay. You don't look. Okay, so it's a minus here. Yeah, it's a minus here. So this is minus a negative term if the Kraft inequality is correct. So this is greater than, minus a negative term is plus a positive term. So this is greater than just the entropy of x. So this is just the entropy of x, for those of you who don't remember. Okay, so what we got is something very fundamental and very simple actually to prove, but actually very important. So we got a theorem, which is known as Shannon's first theorem, or first coding theorem. First coding theorem, which tells you that the expected length of any uniquely decodable code is bounded below by the entropy of the distribution. Okay, this is what it is. Okay, so this is interesting. Why is it interesting? Because it relates to things which come from entirely different domains. One of them is the code length, which is something physical. I mean, how many bits you actually capture on your disk. And the other one is the statistical property of the distribution. Okay, so the next question, which I'm not going to discuss too much, is how tight is this bound? I mean, can I make it as close, as tight as I want? So a bound is a bound. I mean, maybe the entropy is much, much larger than equal. So you can already see from this idea that for special trees, this will be as tight as I want. It will be exactly the entropy. Which, when exactly? So actually, you know when is this bound tight? Precisely where the inequality of the DKL is 0. Okay? So what gave you this inequality is this inequality, the fact that D is greater than 0. When is D going to be 0? In two conditions. So when is the tight bound? The bound tight, sorry. When Q equals P, and when this is 1. Yeah. Okay. So tight is the bound is tight with these two conditions. Tight. Okay. If and only if. I mean, if either one of them is not true, then it's not tight. Okay? Now, what it means by, so the first one means that the Kraft inequality is exactly 1, which you can see actually happens in trees which are completely what we call exhaustive. I mean, if all the leaves are used, as code words, not only part of them, all of them, then it's the Kraft inequality has an equality in it. Okay, so this is a condition actually not waste code words. Use all of them. So you can see that And the second one is essentially telling you this condition. So this is the condition that all the code words are used, and this is the condition that I can write as Lx equals minus log 2 of P of x. Of course, this is a very special condition. It's a very special condition because it seems that most distributions will not obey this. So essentially, it tells you that P of x, if you want, P of x is exactly 2 to the minus L of x. Okay, so this can happen only if your distribution is made out of powers of half, because L is integer, okay? So for example, a distribution which is half, quarter, quarter, or half, quarter, 8, 8, or things like this will exhaust it. This is what we call dyadic distributions. But the point is, and this is something I'm not going to show, is that you can get as close as you want to such dyadic distributions if you take long enough extensions of the code. So if you don't encode only single letters, but include pairs of letters and so on. If you take long blocks, then you can make this bound as tight as you want. Symptotically tight. Okay, so this is really the nature of coding theorems. They're always asymptotic in some sense. In some sense, it's telling you the entropy is really the only thing you care about, as the entropy is the lower bound on the probability distribution of my data. Wow. Okay. So how is this related to description length? So now go. So this is everything I have time to say now. I can say a lot more about it, but we have 2 minutes. So I want to relate it to description of the data, and this is what I call the MDL idea. So let's say now that I want to describe you the data. Let's say you have clustering, you have many clusters or have data, and I want to send it to you or to store it in the shortest possible way on the disk. Okay? What should you do? So essentially what Shannon told you, encode the data in the shortest possible way, which means build a code like this. For this, I need the P of x. So what should I do in terms of modeling? So if I have P of x, this is what you should do. May not be so simple to do, but now how I relate it to learning or to fitting models. So imagine that in the clustering problem, this is the easiest for you to imagine, I think. You have these clouds of points, okay? You have these clouds of points. And I want to tell you, if you do this encoding in 2 steps, I first give you the clusters, and then I encode every point with respect to the cluster which it belongs to. So what do I do first? I first send you the distribution of the clusters. If it was Gaussian, let's say I give you the parameters of the model. I send you the mu's and the sigmas of each cluster, and then I'm telling you this point belongs to this particular cluster, which you can actually find yourself now, and encode the point with respect to the Gaussian of the cluster. So this is called a 2-step coding procedure. I first describe a model, which will give me a distribution, and then I encode with respect to this distribution. Now, what will be the description length of the data if I want to send it to you like that? What it will be? I want to send you the data, but I first send you the model, and then I send you the data given the model. The model is a statistical model. It's giving me a distribution. So I know that once the model, so essentially what I'm doing now is parametric encoding. So I have P of theta. I'm sending you encode theta, and then encode first encode theta, and then encode x given theta.